So here we have a line that has an evenly distributed charge of Q, and we want to find the electric field here at point P. Now, here I have the standard equation of an electric field, where we're going to be using this to find the electric field here at point P. But before we can start messing around with this, let's just mess around with the diagram a bit. So let's just assume if we were to take a small portion of this wire, so this small portion is going to carry some charge d of Q, but it's also going to have some height d of Y. So I'm just going to have d of Y. But keep in mind that this would be a really thin wire. So I just have added thickness here just for the sake of the diagram. But now that we have this, the distance from this line segment to point P is just going to be R. And the distance from point P to the center of the wire is going to be X. And now for the last assumption that we're making is that the distance from the line segment to the center of the wire, this is going to be Y. So now that we have that, we can start messing around with that. So because we have a change of charge here, dq, we're also going to have a change of electric field. So we would have dE is equal to K dq over R squared. So right now, let's just deal with this d of q. So lambda stands for charge per unit length. But in this case, from our line segment that we have, our lambda is going to be the change of charge over the change of length. But in this case, our length is going to be along the y-axis. So let me just draw our directions here. Our length is just going to be along the y-axis. So instead of having d of L right here, we're just going to put d of y. So solving for d of q, we have lambda d of y is equal to d of q. So now we're just going to make that substitution in. So dE is equal to K lambda over R squared d of y. Now, right now we don't want to start integrating because notice that the electric field created by this line segment or by this little segment that we have is going to produce an electric field going diagonally. And we don't want to integrate right now because of this. Otherwise, if we do integrate, we're just going to be calculating for something completely different. So instead, what we're going to do is that notice how this electric field exerts a field going towards the x direction and then the y direction. So I'm just going to erase that, but just know that that way is the positive x direction. So we have change in our electric field in the x direction, and we also have the change in electric field going towards the y direction, or in the negative y direction. So now that we have that, we're going to make another assumption pretty much. So we're going to take this line segment. So these two, we're assuming that they're identical. So they're going to be the same in magnitude, except that this one's just down here and this one's up here. But now this one is going to exert an electric field going diagonally this way. So notice how if these are same in magnitude, all the electric fields being pointed towards the y direction are going to cancel out. So we're kind of taking advantage of the symmetry here, and we're only going to have an electric field going towards the x direction. So we have dE of y. So yeah, these are just going to cancel out. And realistically over here we have 2 dE of x, but I'm not going to write 2 dE of x because I'm gonna deal with that later. You could write that, but as of now, I'm just going to leave it as dE of x. So these are just going to cancel out. And now we're just left with an electric field going that way. So to solve for dE of x, we're just gonna take the cosine of our change of an electric field. So dE cosine theta, where our theta is gonna lie right there. So at this point, we could just substitute this in. We could just plug that in there. So we could just have k lambda over r squared. And I'm gonna write cosine theta just so I can have dy here in the back. So now we can just integrate both sides. When we integrate this left side over here, we're gonna have just e of x, and now we have the integral of k lambda over r squared cosine theta d of y. Now our k here is just constant, so we could take that out of the integral. And our lambda here, remember that lambda is just charge per unit length. This would be the length of the entire wire. And because our charge is constant, so lambda is also going to be constant. So we could just take those out of the integral. So we have k lambda times the integral of 1 over r squared cosine theta dy. Now, actually right now let's just deal with our bounds. Because we're in the y world, we're integrating from negative a to a. So we'll just leave that as that. And actually, instead of doing that, we're gonna take abuse of the symmetry again. So instead of integrating from negative a to a, what we're gonna do is just integrate from 0 to a, but to compensate for this other half of the wire, we're gonna multiply it by 2. So now we're just left with this. So because we're integrating in the y world, we gotta get rid of this r and theta and get them in terms of y. So for r, we could simply just solve for r and just use the Pythagorean theorem. So here is just gonna be x, the square root of x squared plus y squared. So simple as that. So we have 2k lambda. Now because that is the square root and this is squared, we're just gonna be left with x squared plus y squared. Now for our cosine theta, because of trigonometry, this angle right here is gonna be the same one as this one. So our cosine theta is just gonna be hypotenuse or adjacent, the adjacent side over the hypotenuse side. So we're gonna have x over the square root of x squared plus y squared. So now we can just substitute that in for cosine theta. So now we just have x over the square root of x squared plus y squared d of y. Now to just clean this up a bit, we have e to the x is going to be equal to 2k lambda, and the integral from 0 to a, then we have x over x squared plus y squared to the 3/2. Now this integral you could solve using basic integration techniques. However, I'm just going to use an identity just for time's sake. So when we use an identity, we have 2k lambda, and we'll just have a over, I believe, okay. So it's going to be x times the square root of x squared plus a squared. And now this, and electric field is a vector. So because we already know it's going in the x direction, we're just going to do this. So 2k lambda a, 2k lambda a over x times the square root of x squared plus a squared. So because this is going in the x direction, we're just going to multiply this by the unit vector I. Now this is the answer for the electric field created at some point P due to a line of charge. So yeah, really quickly, what we could do with the answer that we found, we could also find the electric field created by an infinite wire. So if the wire has a length of infinity, pretty much, A is going to be approaching infinity. So to solve for this, we're just going to do E of x is going to be the limit as A approaches infinity of 2k lambda over A, 2k lambda A over x times the square root of x squared plus A squared. So what we could do here is just take out all the terms that aren't A. So we have 2k lambda over x, and it's just going to be the limit as A approaches infinity. We're just going to have A over the square root of x squared plus A squared. So now at this point, because A is approaching infinity, x squared is going to be a really small number compared to A squared. So where at some point x squared is not even going to matter. So all we're going to be left with is 2k lambda over x times the limit as A approaches infinity of A over the square root of A squared. This square and the square root cancel, and this A over A is just 1. So this whole thing right here just equals 1. So now we just have the electric field due to an infinite wire of charge, or due to an infinite wire with evenly distributed charge of Q. So there you have it, and hopefully this video proves helpful. See ya.